we introduced the basic symmetries and fermion content of the classical standard model Lagrangian. Where one of the main technical points is that the left-handed Dirac fields, the left-handed fermion fields transform in a different representation to the right-handed ones under the standard model gauge group, which is locally SU3 times SU2 times U1. Although we actually don't know what the global structure of the standard model symmetry group is. In particular, we don't know if it's just SU3 times SU2 times U1 or quotient of that by a finite group, which could be either Z2, Z3, Z4, or Z6. That's very difficult to determine given the experiments that we're able to do. So essentially, we've determined what the Lie algebra of the standard model is through experiments. So in each family, we have 15 fermions, which are the left and right components of the up quark and the down quark. Although they consist, those are actually 12 different fermions because each quark transforms in the three-dimensional fundamental representation of SU3. Then we have the left and right components of the electron, and then we have the left-handed neutrino field. So that's a total of 15. And the representation that the 15-dimensional representation for the standard model fermions of one family consists of these 5 irreducible representations. And this is how the particles are assigned to those representations. And here I was just emphasizing that we have this structure times 3 for the 3 families. And further emphasizing that only the left-handed fermions in each family interact directly with the SU2 W bosons, which means that right-handed quarks and leptons don't interact with W bosons, and similarly, the antiparticles of the right-handed quarks and leptons do not interact with the W bosons. And we emphasized that here, or the inverse of that statement, if you like, by looking at in the top a W plus decay into a positron and a left-handed neutrino. So this neutrino is left-handed, the positron is right-handed, and that's because it's the antiparticle of the left-handed electron. And then there's a similar structure for W minus decay into this, in this particular channel. So then we have this exercise to calculate the terms involving W plus and minus E left and mu E left in the Lagrangian, and similarly the interaction terms between the E right field and B mu. Actually, I can't remember how far I got last time? Does anyone remember? Can I get past this point? Oh, I think I did. I think I got up to here, maybe. Okay. So, yeah, the quarks transform in the fundamental representation of SU3, and that is generated by 3x3 emission traceless matrices. The space of such matrices is 8-dimensional, sort of 3 times 3 for the emission matrices, -1 for the tracelessness condition. So anyway, that means that there are 8 generators, 8 independent generators, and therefore 8 independent gauge bosons for SU3, which are the gluons. So then, in addition to those, we've got the SU2 bosons and the hypercharged gauge boson. So we've got 12 gauge bosons in the standard model. So given that we've understood the generators of in principle, we can understand the 12 generators of the standard model gauge group. And now that we've been given the fermion representation, in principle, one can calculate the full Lagrangian. But in order to do that, one really has to just be careful with the covariant derivative. In other words, just pay attention to the definition. So here was a couple of examples. If we look at the covariant derivative acting on the lepton doublet, then we have the SU2, the 2-dimensional representation of SU2 here, coupling the fields to the W bosons. And then we have the -I G1 B mu term, which we then have to multiply by the actual hypercharge of the lepton doublet. And the hypercharge of the lepton doublet is -1. So if we set y equals to -1, then this term would actually be plus I times G1 times B mu. I just wanted to emphasize that. And then similarly for the right-handed quarks, since these are, for the right-handed up quark field, it's right-handed, so it doesn't transform under SU2, but it does transform under SU3. So we see the appearance of the gluon fields. And the up quark has hypercharge 4/3. So you have to insert a factor of 4/3 in the last term in the covariant derivative to do the calculations correctly. Okay, so we're going to spend the rest of today talking about the symmetry breaking in the standard model and the Higgs mechanism and also the appearance of mass terms. So what we will see eventually is that the electric charge is given by the formula in the box. So in particular, the U1 of electromagnetism is a particular subgroup of SU2 times U1 hypercharge. And that subgroup is generated by the hypercharge generator divided by 2 plus sigma 3 over 2. And in keeping with that, the photon field is essentially a linear combination of the hypercharge gauge boson and W3, because those are the fields in that direction. And the fact that the U1 electromagnetism is unbroken at the end of the day means that the photon is massless. Whereas the opposite combination is a massive gauge boson, and that's the Z gauge boson. These expressions here are very rough. There's in the actual expression that involves coupling constants and what's called the Weinberg angle, but we're not going to go into that level of detail. But you will when you study the standard model later on in the program. Okay, so what I want to demonstrate now is that the gauge symmetries of the standard model actually prevent all explicit mass terms in the Lagrangian. So that's a really important point, that gauge invariance prevents, gauge invariance plus the representation content of the standard model, in other words, the charges of the fields, prevent you from actually writing down any mass terms. So, first of all, gauge symmetries prevent explicit mass terms for the gauge fields themselves. That's easy to see because, even just in the abelian case, if you have a U1 gauge field, then we know that its field strength is gauge invariant. But if you try to add a mass term, a Lorentz invariant mass term, that would be something like this. And that, if you apply the Euler-Lagrange equations in the Lorentz gauge, I think for some reason I was calling this Coulomb gauge, by the way, when we were studying Maxwell's equation, but it's actually the Lorentz gauge. So I apologize for that, but it's just terminology anyway. So in this gauge, the Euler-Lagrange equations for this Lagrangian are just the massive Klein-Gordon equation for the components of the gauge field. That's why the mass term looks like the way it looks. But obviously, C mu times C mu is not invariant under the gauge transformation. So if you impose strict gauge invariance, then M has to be 0. And that's why the photon is predicted to be massless, which I think we discussed before. Similarly, you can't write down, for example, a mass term for the W bosons because of gauge invariance, the same argument. So that simple argument demonstrates gauge invariance prevents us from writing down gauge boson mass terms. Similarly, we'll see that the charges of the fermions prevent you from writing down mass terms for the fermions as well. So here I'm just giving you a definition. So in 4-dimensional gauge theories, what is called a chiral fermion field is defined to be a spinor field which is in a complex and non-real representation of the gauge symmetry. So if R of psi is the representation, if you then look at the complex conjugate representation, it's not the same representation. So for example, just the standard, any representation of the standard representation of U1, psi goes to e to the I theta psi. is not equivalent to the representation psi goes to e to the minus I theta psi. These are, in suitable normalization, the first one is charge +1 and the second one is charge -1. They're not the same representation of U1. And similarly, the fundamental representations of SUN is not equivalent to the complex conjugate representation. And what we'll see is that it's this non-reality of the representation which prevents you from writing down a mass term. But that, to understand exactly why, it'll take a little while. So one of the exercises we had before was to write down this mass term in the Weyl representation. We have gamma 0 is given by this matrix, and if we work out what m psi bar psi is in terms of the left and right-handed components, we see that it couples together the left and right-handed components in this way. So let's consider an actual example from the standard model. And let's consider the left and right-handed components of the electron and consider the U1 transformation to be hypercharge. Well, the left-handed electron has hypercharge -1, whereas the right-handed electron has hypercharge -2, which is reflected in these two gauge transformation rules. So if we then just look at m e bar e, it's obvious that this is not gauge invariant, because E left dagger has charge +1, whereas E right has charge -2, and they can only be invariant if those two things add up to 0. Namely, that if E left dagger had the opposite charge of E right, and in that sense we're talking about that would be a real representation, because we would have two charges of the opposite sign. But in the standard model, it's simply not true. So the mass term is not gauge invariant. This I think I've already said. So yeah, in order for the mass term to be invariant, what you require is that E left and E right themselves transform in the same representation. And so if this were the case for some U1 symmetry, then the mass term would be invariant. And now it doesn't make sense to compare the representations of a left-handed field with a right-handed field. What we do instead is we convert the right-handed field into a left-handed field, which you can do like this, for example. And then you're comparing two left-handed fields. So in other words, we take the right-handed field, take its complex conjugate, and then we multiply by sigma2 to get something which transforms appropriately under Lorentz transformations. And then you see that this rewrites everything in terms of purely left-handed fields. And if we consider these two fields, E left plus E left prime, then that is actually a field in a real representation if the mass term is allowed. Because E left transforms with some charge Q, E left prime transforms in the representation Q bar or Q star, and the complex conjugate of that representation is Q bar plus Q, which is the same as Q plus Q bar. So this representation is real and the mass term is allowed. Whereas in the actual standard model, under hypercharge, E left is in the charge -1 representation, E left prime is in the representation of charge +2, which and the sum of those two is a complex non-real representation. So this is an important point. So does anyone have any questions about it? Okay, good. I mean, it's one of the most important points about the standard model, actually. So, in other words, mass terms correspond to real representations. We can look at another example that arises in the standard model. Say we forget about the SU2 times U1 symmetry and just look at SU3, the SU3 part. Then you see that if we go back to the standard model representations, where are they? Here. So just ignore the SU2 and the U1, then you see that the left-handed quarks, the up and down, they transform in the three-dimensional representation of SU3, but so do the right-handed ones. So if I converted the right-handed ones into left-handed ones in the same way that I did for the right-handed electron a few moments ago, then those left-handed fields would transform in the complex conjugate representation. So you would have fields in the you'd have the left-handed fields in the fundamental representation, and you'd have the the left-handed fields that you made from the right-handed components transforming in the complex conjugate representation. And therefore, that's a real representation because it's 3 plus 3 star, which is invariant under complex conjugation. So in other words, the QCD part of the standard model, the SU3 part, is not chiral, whereas the SU2 times U1 part is chiral. I mean, that's the sort of language that we use. And yeah, I'll leave it as an exercise for you to check that the quark masses are also not allowed by either SU2 symmetry, by both SU2 symmetry and the hypercharged symmetry. So the conclusion is that the standard model fermions are in a complex non-real representation, and hence no bare mass terms are allowed. In other words, the standard model fermion content is chiral. So what we've seen is then that gauge symmetry prevents one from writing down masses for both the fermions and the gauge bosons of the standard model. This is, I mean, from a physical point of view, it's a complete disaster because, you know, massless particles move at the speed of light, and you wouldn't be able to, you can't form structures like galaxies from them. So this problem is solved elegantly by what's called the Higgs mechanism and the concept of spontaneous symmetry breaking. And I mean, from a pedantic point of view, it's simply all one does is adds some additional fields to the standard model. You include some additional fields, which are scalar fields, transforming in a particular representation of the standard model gauge group. So these fields will be called Higgs fields. We're going to study it first, study this mechanism first in a simplified model called the abelian Higgs model. So we start first with the Lagrangian for a complex scalar field and insist that we have a U1 global symmetry. So I've added up to quartic level the only two interaction terms which are allowed, actually the only interaction term which is allowed in addition to the mass. And what we want to define this abelian Higgs model, we're simply going to gauge this U1 symmetry by the way that, I mean, using the techniques that should now be becoming familiar to you from our previous lectures. So in order to do that, we introduce a gauge field, C mu, with a field strength F mu nu, and we replace the ordinary derivative by the covariant derivative, big D mu, and we simply rewrite the Lagrangian and add the kinetic term for the gauge field. And this new Lagrangian, which is the Lagrangian for the abelian Higgs model, has U1 gauge symmetry now. Now, this symmetry breaking story is all about this potential here. So we're going to study the potential energy of this scalar field phi, this complex scalar field phi. Now, first of all, we can say a few things about the potential. If we look at the way I've defined it, we have to take lambda to be real, because we want the energy to be real, and positive, because if we take large values of phi, then the potential energy is dominated by the quartic term. Sorry, there's a mistake here. It's phi star squared. It's dominated by this quartic term, phi star squared, for large values of phi, and you don't want that to be negative. We need that to be positive in order to have a stable system. But the quadratic term, there's actually no constraint on its sign. It could be positive or negative, even though I've called it mu squared. I'm calling it mu squared for historical reasons, or I mean, it's canonically called mu squared in the literature. But mu squared could be positive or negative. So in that sense, we think of mu itself as being a complex parameter. but yeah, complex parameter, but either purely real or purely imaginary, so that mu squared itself is real. Okay. So in other words, we can choose the sign of mu squared to be positive or negative. So let's consider these two options, and let's consider what we're supposed to do. So the classical vacuum of the theory is actually obtained by constant field values. So the point here is that we take d mu of phi to be 0 in the vacuum state of the system, because otherwise the configuration will break Lorentz invariance. But a constant value of phi, because phi is a scalar, that will give you a Lorentz invariant state, and we want to then minimize the potential energy. So if we do that, we get the classical vacuum. So to minimize the energy, one looks at critical points of the potential with positive matrix of second derivatives. Here I'm being a bit sloppy. One should watch. I mean, what one should really do is take the real and imaginary parts of phi, treat them as real scalar fields, and then you want that the matrix of second derivatives of those two real scalar fields has positive eigenvalues in the vacuum state that you find by solving the first set of equations. Okay. So let's do that. If we compute dv by d phi, when we're just differentiating a polynomial straightforward, we get mu squared phi star plus twice lambda phi star squared times phi, which can be rewritten so that both terms have a common factor of phi star. And that so it factorizes into phi star into mu squared plus twice lambda times phi star phi. Now phi star phi is positive and lambda is also positive. Therefore, if mu squared is positive, the only solution is phi equals phi star equals 0. And it's a unique vacuum, and it's a unique minimum. But if mu squared is negative, we have two types of solution. Either phi is 0, or we have that phi star phi is minus mu squared over 2 lambda when mu squared is negative. Okay, so the situation for mu squared negative is radically different for mu squared positive. So for mu squared positive, I've tried to sketch what the potential looks like. I mean, you can find these pictures in the textbooks, but basically you just have a unique minimum when mu squared is positive, and then badly drawn, this sort of goes out, yeah, sort of goes off to large positive values vortically at large phi. But the important point is there's just a unique minimum at phi equals 0. Now for mu squared negative, it turns out that the phi equals 0 critical point is a unique maximum. So an exercise for you to do is to prove that. But for the other class of solutions, namely phi star phi is minus mu squared over 2 lambda, those are actually minima. and I'll leave it to you as an exercise to show that. Now, it's actually, there's more than one minimum. There's a whole family of minima. So if I take a particular value, phi 0, which satisfies phi 0 star, phi 0 is minus mu squared over 2 lambda, then obviously if I multiply by a phase, e to the I alpha, that's also a solution for all alpha between 0 and 2 pi. Because phi star phi has a U1 global symmetry. Which means that we actually have a circle, a whole circle's worth of minima in this case. So I've tried to sketch what the potential looks like. Actually, this sketch is probably better than the previous sketch from an artistic point of view. So this potential is sometimes called a Mexican hat potential. But what you can just imagine is that that you've got like a hill at the bottom, which is this thing here, but it's a hill, it's a three-dimensional hill, so it has a circular symmetry around, and there's a valley at the bottom of the hill, and all around the valley, as you go out, there's a hillside which goes up. And the valley at the bottom is where we have this circle of minima of the potential. And the top of the hill is a unique maximum of the potential. So what's going on is that the kind of physics that this sort of potential describes is known as spontaneous symmetry breaking, because you have this U1 symmetry, which you can sort of visualize in the potential here, and if you start at the top of the hill, that point is unstable. Under any perturbation, you will fall down the hill and end up at some point in the valley floor. And once you've chosen that point, you've broken the symmetry. So it's, and these type of systems are very, common in nature. You can imagine, for example, a pencil. If it was perfectly symmetric, I could sit it on a flat surface, and if I was careful enough, it would stay there. But under the tiniest, and that system has a U1 symmetry going around it. But the tiniest perturbation, pencil will fall, eventually hit its vacuum state, and that picks out a particular direction, which breaks that symmetry. So that's why these things are called spontaneous symmetry breaking, and why this mechanism is called that. Now, so in this particular case, the U1 gauge symmetry is completely broken once a particular vacuum expectation value is chosen. Okay, so what does this actually mean? Well, to understand what it means, we go back to our Lagrangian. Now that we have understood that we've got this vacuum, well, let's take our Lagrangian, substitute the value of the field in the vacuum, and then let's make some perturbations of the field and compute the terms in the Lagrangian. And so let's have a look at that. So we've got our Lagrangian at the top, and I've just expanded out all of the terms, and at the bottom, we see that we can write it as a sort of kinetic term for the scalar plus the current coupled to the gauge field, plus a quadratic term. Sorry, I keep forgetting to subtract the potential. Plus this quadratic term in which the gauge field is interacting with phi star phi. Or in fact, C mu is interacting with phi star phi with coefficient g squared. Well, what we want to do is start with our vacuum expectation value of the field and have a look at fluctuations of the field around that vacuum. Well, the first thing that happens is that that quartic term, its leading piece becomes a mass term for the gauge field, because the leading piece is phi star phi vacuum expectation value, which is just a number, and in natural units has mass dimension 2. So we get a mass term from this mechanism, and that's very nice, because we know that choosing a value of phi, a non-zero value of phi, is not gauge invariant. But the nice thing is that our Lagrangian is gauge invariant, but the vacuum state of that Lagrangian has broken the gauge symmetry and given the gauge boson a mass in a Lorentz invariant gauge invariant system. So that's really beautiful, and that's the essence of how the problem of mass in the standard model gets resolved. So we'll pause there for our regular break, and we'll come back at 54 past the hour, and we'll continue discussing this mechanism. I'll have to get a charger. Oh, pause. Yeah, just before we restart, I just met Pierre Ramond upstairs, who's here to receive the Dirac medal tomorrow. And I recommend, there's an excellent book about Dirac's life called The Strangest Man, written by Graham Farmelow, in which, well, there are many interesting things in the book, but in particular, there's a really interesting account of a young Pierre Ramond giving a seminar in front of Dirac. I guess it would have been in the early 1980s. All right, let's start the recording. Okay, so we see that this mechanism elegantly solves the problem of gauge boson masses. Let's look at it in a little bit more detail. So if we write the field, so what we're going to do is actually just look at some properties of the potential. You will do this in more detail also when you, in the field theory courses. So let's write the field as, in terms of its real and imaginary parts, sigma and pi, and choose the vacuum to be purely in the real direction, so that sigma has a non-zero expectation value, which is customarily denoted with a small v, which the reason for that is that V stands for vacuum expectation value. And so the expectation value of pi is 0 in the vacuum. So then, you know, the fluctuation of the field is just sigma prime plus I times pi. And so let's substitute back into the Lagrangian. So sigma is just V plus sigma prime. And then you've got the imaginary part going along. So at the bottom, we've just substituted in the expression into the potential. And now we expand it. What we want to do is expand everything out. So we expand this out, and we expand out this square of sum of squares. Oh, there's a typo here, sorry. What have I done here? Oh yeah, just a sec. I'll just rewrite this more carefully. So we expand out the two sets of terms. And what happens is that the quadratic terms in pi actually cancel out. So that's what I'm saying here. So the 2v squared times pi squared cancels with mu squared pi squared when you put in the value of v squared. And similarly, this linear term in sigma prime over here cancels with the linear term in sigma prime over here. So I'll leave that as an exercise just for you to go through. I don't want to go through it now, as we've got a lot of material to get through. So what you're left with is a quadratic term in sigma prime, whose coefficient is mu squared plus 6 times v squared. Plus you've got these quartic terms proportional to lambda, plus you've got a few cubic terms, which I haven't written. And the quadratic terms in the mass terms, essentially for sigma prime, are proportional to, have a coefficient which is minus 2 mu squared. And since mu squared is negative, this is a positive mass squared term. So in other words, sigma prime is a massive fluctuation in this system. And then you've got all the other terms. All right, well, that's what I've said here. Now, the pi field has no mass term at all. And the reason for that is that it becomes part of the gauge field mass, essentially. So a massive gauge field, as opposed to a massless one, has 3 helicity states. And the massless gauge field that we started with has only 2. So Lorentz invariance actually requires that if the theory describes a massive spin 1 particle, that the extra helicity state has to come from somewhere, and it comes from pi. And in fact, if one is so really to study the full spectrum of a gauge theory, one should fix the gauge, because the gauge symmetry is a sort of redundancy in the description of the physics. And one can choose a gauge, which is usually called unitary gauge, in which in fact pi in the vacuum is completely eliminated from the system, and you just have the massive gauge particle. So I didn't say, so sigma prime is sigma prime gives rise to a massive Higgs particle, a single massive Higgs particle in this system. So the low energy mass content of the system in the vacuum is one massive scalar and one massive vector. Are there any questions about that before we go on to the standard model case? Okay. All right, so now we're going to introduce the Higgs field of the standard model. So again, this is a scalar field, big phi. And all we have to do is specify which representation of the standard model gauge group it transforms under. And that turns out to be the 1, 2, 1 representation, namely that the Higgs field is an SU3 singlet. It's a doublet under the SU2 gauge symmetry, and it has hypercharge +1. So in other words, the Higgs field of the standard model is actually 4 real degrees of freedom, because you've got the 2 components of the doublet, which I'm calling phi plus and phi 0. And phi plus and phi 0 themselves are complex fields. So it's 4 in total. Okay, and then up to quartic terms, the only 2 terms you can write down are of the type that we had in the abelian Higgs model, except now instead of phi star phi, we've got phi dagger phi. So there's the mu squared phi dagger phi term in the potential, and the lambda phi dagger phi all squared term. So this, even though this now is this potential is a function of 2 complex scalar fields, so it's more complicated, the structure is basically the same as what we saw in the abelian Higgs model. Sorry, I forgot there's an exercise here, which is just to write down explicitly the covariant derivative on phi, because in the Lagrangian, there'll be a kinetic term for phi, which it's important to understand. So again, for mu squared negative, we have spontaneous symmetry breaking. And we can choose that to be, you can choose that to be in any direction in the SU2 doublet space. And we'll just pick that for simplicity to be in this direction, where phi plus has 0 expectation value and phi 0 has expectation value v. Now, this expectation value breaks SU2 times U1y to U1. And that U1 we will identify with U1 electromagnetism. So let's see why that is the case. Well, let's look at a particular SU2 transformation. Sorry, SU2 times U1 transformation. Okay. In particular, let's look at the 2x2 matrix M of alpha, which is generated by in the hypercharged direction 1/2, and in the SU2 directions, we're going to use the same parameter alpha and go in the sigma 3/2 direction. Okay. So now you can check that that matrix leaves invariant the vacuum expectation value. It preserves the phi 0 direction of the SU2 doublet. And the reason is that when you expand out the SU2 part of the matrix, you'll get a diagonal matrix with entries which are something like, e to the I alpha over 2. Sorry, there's a mistake here. These coupling constants shouldn't be here. Let me correct that. And when we say hypercharge here, this is really e to the I alpha over 2 multiplying the whole 2 by 2 matrix with the whole 2 by 2 SU2 matrix. So the point is that there's a cancellation in the bottom component, and this matrix M becomes just upper triangular. Well, it has a 1 in the bottom right-hand corner, as you can easily check. So in other words, M is generated by the hypercharge of the Higgs field, which is 1 in this particular case, divided by 2 plus sigma 3 over 2. But we put the y in because when that particular matrix acts on the other fields, the value of y will be field dependent, depending on which representation that they transform it. So this explains our previous formula that electric charge is generated, the U1 electromagnetism is generated by this particular combination of Lie algebra generators. And also shows that the Higgs vacuum expectation value is preserved by a U1 subgroup of SU2 times U1. I'll just say that it doesn't matter. I mean, I've done it in the simplest way where we've chosen the direction, chosen a particular direction. It doesn't matter which direction you choose. There will always be a U1 which is preserved under the there will always be a U1 subgroup which preserves the vacuum expectation value, no matter what the vacuum expectation value is. Are there any questions about that?
It's still not clear to me how let me see. So the M transformation preserves the vacuum, but there's not. So how to claim that it after the spontaneous symmetry breaking that the SU2 times U1 will becomes U1, because this only true for the vacuum case. It's not even clear that it will hold for Higgs in general, not even other particles. Right?
No, it is clear, because the only thing in the whole theory which breaks the gauge symmetry is the expectation value. So that's all you have to check. The gauge symmetry, so you could, I mean, you'll see that if you try to take the Lagrangian and look at which generators are gauge symmetries, you'll see that that exercise boils down to just checking, doing this explicit check. That's all you have to do. Because it's the only thing which breaks the gauge symmetry is the expectation value of phi.
Yeah, that's right.
Any other questions? Okay. Now, as a result of this symmetry breaking pattern, since SU2 times U1 has dimension 4, we started off with 4 massless gauge bosons. And since U1 has dimension 1, it means that 4 minus 1, i.e. 3 gauge bosons, become massive due to this mechanism. Since phi, big phi, sorry, has 4 real degrees of freedom because it's a complex doublet, 3 of these are like the pi's of the previous model. So we'd have like 3 quote unquote pions. They become the 3 required helicity states for the massive gauge bosons. And the 4th one remains as a massive scalar field with a positive mass squared, and that its excitations correspond to the physical Higgs boson. This is what we've said before, just I'll re-emphasize it. So what you end up with in the end are 3 massive gauge bosons. One is the Z, which is some linear combination of the hypercharge gauge boson and W3. And then you get W plus and W minus, which are actually these, in the way I've defined it, these 2 linear combinations of W1 and W2. They're the ones which appear in the off-diagonal components of the covariant derivative. The reason it's these 3 that we write is that these are actually the mass eigenstates of the Lagrangian expanded around the vacuum. So we're not, as I said, I didn't want to go into the details of this because you will do the details of this when you do the full standard model. This is more like a sort of introduction and overview. Okay, so that explains how the gauge boson masses arise, but we still haven't finished because we've got to understand the fermion masses. And the Higgs mechanism also solves the fermion mass problem. The fermion mass problem that we mentioned earlier. Well, now that we've introduced a new field, phi, we have to consider possible new gauge invariant terms in the Lagrangian. And in particular, there are so-called Yukawa interactions. So a Yukawa interaction is essentially an interaction between a scalar field and 2 fermions. And it turns out that new gauge invariant interactions are possible. So for example, here is an example of an interaction between the Higgs fields, the lepton doublet, and the right-handed electron. And this is gauge invariant. For example, the hypercharge of the right-handed electron is -2. The hypercharge of the Higgs field is +1. And the hypercharge of the conjugate of the left-handed doublet is charge 1. So you see that under a U1 hypercharge transformation, this product of fields is invariant. similarly, since the lepton doublet, since the conjugate of the lepton doublet transforms in the conjugate of the fundamental representation of SU2, and phi transforms in the fundamental representation of SU2, there's a gauge invariant product between them, which would be, you know, 2 dagger times 2. And since SU2 is unitary, that's gauge invariant. So you can check that explicitly as an exercise. Now, if you write this out in more detail, we get, if I take that particular coupling, we get, and you work out all the components, etc., you get these two terms. And so you see, in the vacuum, where phi plus is 0 and phi 0 is V, the second term on this line leads to a term which is lambda E times V times E left bar E right, which is a mass term. Actually, strictly speaking, we should write, you know, in the full model, you write this plus emission conjugate to get the full mass term. So this is actually how in nature, although this particular coupling, as we'll discuss, has not been measured yet, but this is how in nature the electron mass arises. As we'll discuss momentarily, for some of the other fermions, this coupling has actually been measured at the Large Hadron Collider experiments.
Can I ask one question?
Of course.
So here we actually choose the vacuum at the beginning. So the vacuum of phi plus is 0. But what if we choose another kind of vacuum?
As I said, you could then just redefine the fields. So if I'd have, let me just say I just chose phi to be AB, okay? This is some direction in a two-dimensional space. This is the direction AB. I can just take the orthogonal direction, whatever that is, and that would be the phi plus direction. So I just did, for simplicity, I chose them to be orthogonal to begin with, but there's always an orthogonal direction you can choose. So in other words, the statement is, if you've got SU2 times U1 Y and some field transforming in this representation, a generic value will always will always be preserved by a U1, some U1, and then that U1 is what you call U1 electromagnetism. Okay.
So the combination of the W boson that you wrote before, it already makes sense when we actually choose the vacuum 0V. Is it right? I mean, if we choose another vacuum, then we have to rotate the W boson in another.
Yes, that's correct. That's correct. That's correct. It's just given in the textbooks. It'll typically be done this way just for convenience, but you can always bring it into that form by a field redefinition. Okay.
Yeah, I understand. Thank you.
Yeah. So we have this beautiful fact that without the Higgs field, the fermions and gauge bosons have 0 mass, but in the vacuum, the mass terms naturally arise from gauge invariant operators. And this is true for all of the leptons and quarks. So as an exercise, I want you to work out what the Yukawa couplings are for the quarks, the up and down quarks. And in general, the fermion masses have this formula where V is the same for all of the fermions, because there's just one Higgs doublet in the standard model. So what this means is that heavier fermions, so since V is the same for all, there's only one V, which is actually, in the way I've defined it, V is now sort of measured to be 246 GeV, just so you get an idea of what the number is. So in order to fit the observed values of the fermion masses, we just have to pick the values of these Yukawa couplings, which are just their dimensionless numbers. And you see that heavier particles will have bigger Yukawa couplings and lighter particles will have smaller couplings. So that means that the heavier the particle in the standard model, the more strongly coupled it is to the Higgs field and the Higgs particle. So we'll end with some, we'll end the course with some real physics. So because of these Yukawa interactions, which are all of the form, phi times fermion field bar times fermion field, the Higgs can decay to most of the light fermions in pairs. In fact, all of the light fermions except TT bar and the neutrinos, according to the standard model. And I've ordered these fermions here in decreasing mass. So the bottom quark is the heaviest of the ones in this list, and the electron is the lightest one. So the standard model predicts that the Higgs will decay to, right, in quantum physics, we do statistical experiments, right? So given one Higgs, you can't say what it's going to decay to if you created one somehow. But you can say, given 5 million Higgses, what the probability is that it will decay to, say, CC bar and compare that to how often it will decay to DD bar. And so the statement is that the highest, the decay of the Higgs is dominated by BB bar, and for 125 GeV Higgs, this is close to like 60% or something. And then, as you go down in mass, the probability goes down, and the ratios of these probabilities is actually controlled by the square of the masses of the particles. So, for example, the ratio of decay widths from phi to BB bar, phi to CC bar, I'm writing equality here, but this is at tree level. So, I mean, this means, dominated by the ratio of the bottom quark mass squared to the charm quark mass squared, which is something like 4 or 5 squared. It's a bit less than 5 squared. And that's consistent within uncertainties for what the probabilities are calculated to be. On the other hand, if you look at these numbers, so the Higgs decays most of the time at, the real Higgs, meaning the 125 GeV actual Higgs that's been produced at the LHC, does decay most of the time to bottom quarks. Now, to calculate this probability means you have to also take into account its decays into W's and Z's and so on, which I haven't really spoken about. But the ratios of the fermion decays are sort of just controlled by the ratios of the Yukawa couplings squared, which is the same thing as the ratios of the square masses. Just to bring in the symmetry structure of the standard model, the ratio of phi to BB bar compared to phi to E plus E minus is not just the ratio of the masses, but there's a factor of 3, because there are 3 B quarks, but there's only 1 electron. Modulo helicity states. And that ratio is like 3 times 8,000 squared, because the B quark is like 8,000 times heavier than an electron. Which means the probability of a Higgs decaying to E plus E minus is tiny. It's like much less than 10 to the minus 7, probably 10 to the minus 8, 10 to the minus 9 or something. So this one has not been measured. This is actually measured. This is actually measured. And this one we have evidence for, but have not yet conclusive evidence for. So these measurements, so in other words, one does proton collisions at the LHC, and some fraction of the time you produce Higgs bosons. The Higgs boson, the lifetime of the Higgs boson, is some tiny number. It's like, I don't know, it's less, certainly less than 10 to the minus 22 seconds, probably 10 to the minus 23, 24 seconds. So it's tiny lifetime. It will decay very quickly into whatever it's decaying into. And then the particles into which it's decaying, they themselves may decay further. And then from those final states, the final states, which could be electrons, hadron jets, and neutrinos, and photons, and muons. Those are the sort of things that actually get measured, and then you try and reconstruct the particle that actually decayed, or whatever was in the original event. So it's a very difficult process overall, but the Higgs decaying to bottom quarks and tau leptons has been measured now with very high significance, which means that those Yukawa couplings that we talked about in this theoretical framework standard model have been measured, and as has the mass of the Higgs boson, and its couplings to the gauge bosons have also been measured to some extent. So the beautiful thing is that this model actually is describing the world of elementary particle physics in a, as far as we can tell, in a very accurate way. So I think we'll finish the course there. I'm going to pause I'm going to stop the recording actually. And we can have some questions, and then I'll try and figure out what we're doing next week.
Professor? So why the Higgs must be a singlet under SU3? Is it because the gluon is measured to be massless, so we have to force it to be singlet, or any other motivation?
It's a very good question. So we can't directly measure the gluon mass. Did I explain at some point in earlier lectures about hadron jets and stuff like that? Because I don't remember. Well, let me try to answer the question anyway. So the strong interactions, which are the SU3 interactions, they're called strong. They're actually strong at low energies. So, you know, when we write Lagrangians, you know, when I write, for example, the QCD Lagrangian, and I add the coupling to quarks. You know, in this covariant derivative, we've got G3 which is the strong force charge, if you like, or coupling constant. Now, it turns, as you all learn in quantum field theory, these couplings, I mean, any gauge coupling in any gauge theory, unless there's no interactions, is dependent on energy scale. So actually G3 is a function of some energy scale M. Okay, so normally we write it in terms of the corresponding fine structure constant, which is defined as the square of the coupling divided by 4 pi, because this is the analog of alpha electromagnetism, like the fine structure constant for electromagnetism. And all of these things are energy dependent. And the reason for that is that, if you want to measure, for example, the charge of a quark, so the charge of a quark should be G3 times, so here I'm talking about the strong charge of a quark, not the electric charge. So if I want to measure this G3, I have to measure, the coupling in this Lagrangian somehow. And the point is that a quark, because of the interaction between a gluon and a quark, and so because of the interaction between gluons and themselves, the ones that we mentioned before, a quark is not a quark just by itself. It's surrounded by a virtual cloud of, you know, a Q bar pair can pop up out of the vacuum at any time due to just the uncertainty principle. So it's actually surrounded by Q bar pairs of different flavors. And these guys can then, they'll live for a short time, annihilate, and they can turn into gluons, and then the gluons can split into additional Q bar pairs. So all particles that participate in gauge interactions of any kind are surrounded by these virtual clouds. Now, from a long, long way away, if I'm measuring from over here, I'm not going to see that. I'll just see the overall charge of this cloud. But if I go closer and closer to make my measurement, and to go closer and closer, I have to increase the energy scale, because you're going to shorter and shorter distances. You know, you're using a more powerful microscope as you get closer and closer. You become sensitive to this virtual cloud, and it means that what you thought was the coupling actually depends on energy scale. So and that's true also for the electron, I mean, for the usual alpha electromagnetism. You know, it's equal to like 1/137 or whatever it is at very low energies. So for experiments which are not, I mean, so it's experiments at low energies, let's say, but at higher energies, the value of alpha is actually different. And these are also effects which have been measured, by the way. And in the case of QCD, what actually happens is something like the following. I'll draw this very badly, but so there's a scale. So at very high energies, alpha goes to 0. And this is called asymptotic freedom. And Gross and Wilczek and Politzer got the Nobel Prize for this calculation some years ago. But at lower and lower energies, alpha starts getting stronger to a point where we can't even calculate it anymore. So it becomes kind of order 1. And if you get alpha of order 1, it means you can't use Feynman diagrams anymore to calculate stuff. So the strong force has this property that at some particular scale, which is of order 200 MeV approximately, the interactions become very, very strong, which means that, you know, if you have a quark and an antiquark, they want to form a bound state. As opposed to, in other words, it's energetically favorable for them to bind together, as opposed to a state of 2 free quark, or a quark or an antiquark pair. Whereas at high energies, they can move around freely, but at low energies, they can't. So if you then look at all of these, so, you know, basically this this means that quarks have never been observed as free particles. They've always been observed in these bound states, which are mesons and baryons. So low energies, quarks and gluons and antiquarks. Form bound states. And it turns out that all of these bound states are SU3 singlets. SU3 bounds. You know what I mean? All of these bound states are observed to be SU3 invariant. So from an observational point of view, the SU3 symmetry is not broken by the vacuum. One can also overcome these difficulties of not being able to do calculations like, traditional quantum field theory calculations in this strong coupling regime by doing computer calculations, which is called lattice. This is the subject called lattice gauge theory. So lattice gauge theory can actually, in some sense, analytically solve quantum chromodynamics, and there, they also established that the SU3 symmetry is unbroken. Sorry, so yeah, the answer to your question took a little while, but we learned something along the way.
Yeah, thank you. That's clear. And one last question. So why should we choose the Higgs to be a scalar? So I think we can also choose, for example, a right-handed fermions for breaking symmetries using the same mechanism. So why have to be a scalar?
It has to be a scalar because Lorentz invariance is known to be a symmetry up to pretty short distances. If you gave an expectation value to a fermion field, it would break Lorentz invariance explicitly because it carries a spinor index, a Lorentz label. So that's why you can't. That's why the scalar is the only possible choice. So, in other words, the vacuum. If you broke the symmetry with a field value where the field transforms in an untrivial Lorentz representation, then you would break Lorentz invariance.
But why didn't the vacuum also transform under the Lorentz transformation along with the field? So if it is allowed to do that, then the symmetry would not broke the Lorentz symmetry.
No. Imagine you have some field, okay, F. No, let me not call it F. I'll call it. Well, let's say it's a Higgs field, but it has, let's say, it has a standard Lorentz label just for. And imagine this is non-zero. So then this is actually equal to some. What's a good notation for this? Well, to some vector. Okay. Well, this vector, because it would be a vacuum expectation value, is just some constant vector field. So that constant vector field chooses a particular, particular direction in space-time. So, you know, Lorentz symmetry is explicitly broken by the vacuum state. And I mean, it could have been that way, but it turns out that our vacuum looks pretty Lorentz invariant as far as we can tell.
So the vacuum also can transform under the Lorentz transformation?
Well, then it becomes a question of definitions, because, I mean, if you start with a Lorentz invariant field theory, practically by definition, the vacuum should be Lorentz invariant. But, if you want to give up Lorentz invariance, then, you know, as soon as you sort of start entertaining this type of situation, you have to then introduce, you have to be open to introducing all possible interactions which are not Lorentz invariant. So the Lagrangians we started with would have to be modified to allow for, you know, for example, you could then have a term which was, because this vector is some specific vector. So then you could add, you know, for example, V mu, D mu of some other field, which would be a very strange term. So it's not that we know that Lorentz symmetry is a symmetry of nature at a fundamental level, but we're pretty confident that it's a symmetry down to very small scales. So any such violation of Lorentz invariance, this has to be really very small, if it exists in nature.
Yeah, I'll try to think more about it.
Okay, so well, let me just see if there's any other questions.
I just wanted to ask about the references. Is Peskin still the reference for this part?
I didn't really use a reference, but yeah, you could. I mean, this material, well, the Higgs stuff is in Peskin, I think. Some of it is anyway. The stuff on the potential and the company, I mean, it should be there, but you just be aware that I think, for example, Peskin, you know, where I write V equals mu squared phi star phi plus lambda, Peskin may write something like minus mu squared over 2 or something. So there'll be a sign and coefficient changes, but it should be there in Peskin.
Okay, and there was this part where we did when we just introduced gauge theories and we talk about coupling fermions with electromagnetic interactions.
Yeah.
I was trying to search it in Peskin, but I didn't find it. I don't know if you have a reference for that.
Oh, I thought it was in there, the coupling. I mean, he does the non-abelian case, no?
Yeah, right. So the Peskin was for the Dirac equation and non-abelian gauge theories. But when we introduce gauge theories, we talk about electrodynamics a bit.
Yeah, but so the stuff on like F mu nu and so on for electromagnetism, that's in Landau and Lifshitz. And I think I must have exactly the same convention, but that's before we couple to particles.
Yeah, yeah.
And then the coupling, I mean, you could just take Peskin and go to the, just specialize to an abelian gauge group with one generator for that. It's the same.
Oh, yeah.
Okay. Any other questions? Okay. Yeah, so next week, as I said, we'll arrange 2 tutorials. The exercises, if you could get them in, the remaining exercises by Tuesday, that would be great. There's some, originally I was planning the tutorials to be on Tuesday and Thursday, but I was informed today that because there's some meetings going on of our scientific council, that we're not supposed to use this room. But I think we'll go ahead with the plan of Tuesday and Thursday. It's just that the tutorial on Thursday, Ida won't be in this room. But she'll be maybe in, yeah, maybe she can do it from her office. There's a blackboard there anyway. Okay, and then I'm thinking for the exam, to be on 11th of November. Okay, so possibly what we'll do is we'll, once you're, we'll have a look at the situation around the 8th and 9th of November. I'll maybe send you an email and ask if you want to have if you would like to have a revision lecture or a session with me that week, just to, since you will have been maybe focusing on quantum mechanics the week before or something. But I'll, so that we can arrange like an optional sort of tutorial / revision at the beginning of that week. But I was planning to have the exam in the afternoon of the 11th of November. Okay. So I hope you've enjoyed the lectures, and I certainly have enjoyed preparing them. It's been fun. And